So far, we've only looked at yield surfaces of the form like that. This is J2. Okay. So let's look at a different one. So I'll just say other yield surfaces. So there's one that is known as the maximum shear stress criteria, or also known as Tresca. Tresca criterion. And it is the maximum of these arguments and if you recall, when we looked at the Moore circles, right, we have like so the state of stress is always in this region, and this is sigma 1, sigma 2, and sigma 3. So if you recall, I said that this here is tau max, right? So basically, you're going to find the maximum of any of the principal stresses. That's going to give you the maximum, value of tau max, so therefore the maximum shear stress. So that's why it's called the maximum shear stress criterion. There's also the way that you can write this in terms of the invariance. It's a little weird, but we have 4 J2 cubed minus 27 J3 squared minus 9 J2 squared plus y minus 6 J2 y to the 4th minus y to the 6th equals 0. So that is the maximum shear stress criteria in terms of the invariance, like we wrote the other yield surfaces in terms of J2, right? But now you notice that this one has a J3 in it. So it's not just a function of J2, it has J3. So if you remember what J3 is, the determinant of Sij, where the determinant is, if I use this symbol sigma d for the deviatoric principal stress, then it's just the multiplication of the 3 principal stresses. And so we looked at before in a uniaxial tensile test, the deviatoric stress at the point of yielding is like and so J3 in this case, as I have it written, J3 is 2/27 y cubed, and this is in a actually, sorry. The way we wrote this before was this was a positive number, positive 2/3, and this was negative, and this was negative, right? So this, I don't know if I've said it before, but everything we've done or everything we're doing in this class uses tension positive, right? So this is a tensile test where we're pulling on the bar and it's yielding, okay? But if we flip it around and basically run the same test in compression, so we squeeze it instead of pull on it, then these signs flip, right? So then we get a negative there and a plus and a plus. And so then what you'll see is that J3 becomes minus 2/27 y cubed. So this is in compression. So what J3 can be used for, or why it appears in the yield function, is that it can be used to delineate or have a yield surface that's different in tension or compression, right? And we'll see an example of that shortly, but that's what J3 could be. So this Tresca criteria, if you look down the hydrostat, as we've looked at a lot of these yield criteria, so sigma 1, sigma 2, sigma 3. So before we have that, the von Mises yield criteria is a circle. Then the Tresca criteria basically overlaps in some places with this circle. But is actually, I'll draw it in a different color. It's actually this blue line. Like that. So this is Tresca. And so it's close to the J2 yield surface, but not exact. And it turns out that for a lot of brittle materials, that shape of yield surface actually does fit the data better. So if you did data, if you collected data in different loading paths, right, meaning like different states of tension and compression, then you would find that the material would fail or yield not at the circular lines, but at the straight ones. So it's a very subtle difference, but for a lot of brittle materials, it actually does describe the yield surface better. I'll also just try to draw it in in the 3D view. So again, if this is sigma 1, sigma 2, sigma 3, and this is that hydrostat, right? This is the line, sigma 1 equals sigma 2 equals sigma 3. Then that Tresca yield surface is going to look something like this. So it's still infinite in both directions, but it just has that hexagonal shape. One thing that you'll notice about the Tresca, obviously, is, when we talk about a flow rule, right, we have to use this associated flow rule that's associated with the yield surface. Or in other words, it's normal to the yield surface. But you see at the corners, at the very corners, right here, you can have small changes in, depending on where you're at on either side of that corner, you can have small changes in the state of stress that vastly change the direction of the flow rule, of the associated part of the flow rule. And in particular, there's difficulty right at the corner, right? Because the normal's not defined at that sharp corner. And so this is the reason that computationally, it's rare that people would use the Tresca yield surface because, well, it's not rare. It's harder to use than the von Mises. So you have to have a really, the von Mises or the J2 surface, because you need to have a really good reason. Like your data better fit that hexagonal region very well in order to choose that one over the smooth one, because computationally those corners are going to cause you difficulty in your return algorithm. And so, you better have a good reason to use that one over the, and we'll see more about